The Missouri S&T Mars Rover Design Team, after our university's closure in March, has picked up where we left off through the summer. After 8 months of remotely planning, remote designing, and socially distant manufacturing, we're proud to introduce our 9th rover, Aurora.
Aurora'S custom suspension platform, called Lynx, was designed from the ground up to enable precise movement while maintaining high durability. Consisting of 4 independently stabilizing aluminum and carbon fiber linkages, the suspension is supported by custom-designed gas springs which dampen the impact of terrain to the rover's body. Custom-built steering units equipped with brushless motors enable full 360-degree rotation of each wheel. Aurora can drive sideways, perform point turns, and drive in smooth arcs, allowing it to circumnavigate obstacles with ease. Finite element analysis simulations were performed to ensure each link and the suspension as a whole can withstand a 1 meter vertical drop, a forward impact at max speed, and lateral impacts at half speed. The rover's core includes gimbal masts with multiple 2-axis cameras as well as an auxiliary attachment mount for autonomy, manipulation, and science modules. We believe that these innovations create a suspension that is optimized for the specific tasks we will be facing at URC.
We designed Aurora'S electrical system to be a decentralized and modular platform, allowing each PCB to be easily replaced in case of a fault. To ensure safety, every board undergoes a thorough unit test confirming all functionality, including integrated current sensing with overcurrent detection and mitigation. Our 8S9P lithium-ion battery pack includes temperature, current, and voltage monitoring. It is built to last 2 hours, which is sufficient for competition tasks.
For the equipment servicing and extreme retrieval tasks, the rover utilizes last year's manipulation system, which consists of 3 2-axis differential joints and a dual end effector platform. Brushless motors provide high torque while maintaining a low weight. Worm gears in the base and elbow produce near-zero backlash, resulting in increased fine joint control. Each motor has an incremental encoder and each joint has an absolute encoder. Together, these enable granular control of each joint, resulting in smooth end effector movement. The dual end effectors provide multiple options to grip or interact with objects in competition tasks. The arm is able to flip switches, pick up rocks, and type on keyboards, enabling success in high-precision applications.
Aurora is controlled by an all-new base station with a custom 4-window vertical graphical user interface. Its core features include embedded camera feeds and a dynamic 3D model of the rover that shows its orientation in the field. Our new map component allows the operator to click and drop waypoints for better course plotting and navigation. A real-time network Pingmap provides a quick view of latency between the base station and the rover. To ensure reliable communication, Aurora is equipped with a 900 MHz antenna for non-line-of-sight applications at ranges up to 1 km and a 5.8 GHz antenna for increased bandwidth at shorter ranges. Together, these systems provide detailed control and overview of the rover. Aurora'S Autonomy stack employs an internal navigation system with onboard GPS and IMU to provide the position and orientation data of the rover. Fused 3D point cloud segmentation provided by a Z camera is used to recognize and avoid untraversable terrain. Once a waypoint is reached, the rover engages a search pattern and uses a cascade-based computer vision classifier to detect and track AR tags. For testing and verification of code functionality, we developed a 3D simulation environment to prototype changes before they are deployed.
Our science system uses onboard chemical experiments and gas sensors to analyze soil for evidence of life. A vacuum cyclone chamber collects samples and deposits them into one of 12 test tubes contained in a Geneva-driven carousel. Peristaltic pumps then administer up to 3 separate chemical solutions into test tubes to identify amino acids, nitrates, and lipids. The vacuum nozzle is mounted alongside a sensor box containing a 395 nanometer compact spectrometer, a UV light to determine fluorescence, and digital sensors that detect methane, carbon dioxide, oxygen, ammonia, and nitrogen oxides. Camera feeds and sample-specific sensor data are streamed to the base station to help the operator determine whether extinct, extant, or no life is present in each of the samples.
In the final months before URC, our travel team will practice competition tasks in their entirety to refine our systems and approach to each mission. Even with the limitations imposed by COVID-19, we're confident in our ability to succeed at the University Rover Challenge. On behalf of the Missouri S&T Mars Rover Design Team, we thank you for your consideration.